Hi, everybody. So this is our first video of Chapter 2. We're going to go over kinematics and derivative calculus in this chapter. So first, we're going to go over position versus time graphs. So the first idea that we would do in class is to walk the motion of this position versus time graph. So you have position on the y, time on the x. Position is in meters, time is in seconds. The actual graph, I guess the actual data, is in the red line, the red parabola. The slope is shown in blue. I think that's supposed to be blue. That is the slope from one point to another, from A to B, then from B to D. Then the green line is the slope at point C, and we'll talk about instantaneous slope today, or what's called a tangent line. So first, pause this video and walk the motion of this position versus time graph. So what you would do is you would start at a point, then you would go, it looks like you would go backwards, right? Because it goes negative. So you'd go to -2 meters in the first second. Then over the next 2 seconds, from the first second to the third second, you would travel 2, 4, 6, 8 meters. So pause the video and go backwards 2 meters, then forwards 8 meters in the appropriate time. Back 2 meters in 1 second, then forward 8 meters in 2 seconds. You'll probably have to run it, or at least give it a jog. So pause your video, do that now. And now that you're back, number 2, when is the velocity 0? So let's look at this graph. How do we know what the velocity is on a position versus time graph? So velocity on a position versus time graph can be described as the slope. So slope is going to be your velocity. Because slope is rise over run, right? Slope is your change in y over your change in x, right? So if we translate that into this graph, you would have a change in position over change in time, right? Position is your y value, time is your x value, and the change in position over time is velocity. So if we look at this graph, where along the graph is the slope 0? And there is only one point where the slope is 0. Now, most often when you're looking at slope, you're looking between 2 points, right? So if we look at from A to B, we can see that there is a slope of -2. That is on our screen. Right there. Let me move that camera right there. There we go. So I can move back and forth. So slope of -2 meters per second from A to B. Now, if we want to look at instantaneous slope, we have to use what's called a tangent line. So a tangent line is when you look at a slope. Now I'm going to go into the next slide real quick to give you a demonstration. Say we have a parabola and we want to find the slope at this point. What you can do is you can start way out here and connect those 2 lines, right? That's the slope. Let's say that is from point 1 to point 2. Okay. Now, if we want to know the slope at point 1, we need to move point 2 closer to point 1. So as we move that closer and closer and closer, now we have the slope from 1 to 3, right? And you can see that that line is getting shallower. Okay. Not a very good parabola. Let's try that again. Okay. I've got point 1. Now let's move that dot even closer. And that line continues to get shallower from 1 to point 4. And then you try that again from 1 to point 5 until you get to point 1. and that would have a flat slope at the bottom of a parabola. Now this is just pure for parabolas, but that is how you find a tangent line. You find the slope between 2 points, and you move that one point closer and closer until you get a slope that only touches the graph at that single point. So back to number 2, when is the velocity 0? Well, that only happens right there at point B. That's where the velocity is 0. So on number 2, point B is when the slope is 0 meters per second. You know it's meters per second because slope is rise over run, position over time, meter per second, meter over a second. Now, number 3, if the average velocity of a particle moving in a line is positive, can the instantaneous velocity ever be negative at any time in that average, I guess, wherever you're calculating that average? So let's say the average velocity of a particle is positive. Could the instantaneous velocity ever be negative even though the average velocity is positive? Now, pause the video real quick and try and think of a scenario in which an average velocity could be positive, but an instantaneous it could be negative. And now that you're back, an example would be our graph right here. Now, if we look at the average velocity from A to D, okay, that starts right here, goes up to here. If we draw a line connecting those 2 points, that would be the average velocity over that time. Now, that's obviously not the instantaneous velocity for the whole problem or for the whole time frame, but that's the average velocity over those 3 seconds from point A to point D. Now, that is a positive slope, right, on that line. But we can see from A to B at all of these points in here, we've got a negative slope on that parabola. So the instantaneous velocity from point A to point B appears to be negative. However, over that entire time frame, the average of the velocity is going to be positive. So now we're looking at the difference between average velocity and instantaneous velocity. And don't get those confused. Instantaneous is the velocity at that moment. Average velocity is the velocity over a period of time. So for example, say you're driving from Oklahoma to Tulsa, Oklahoma City to Tulsa, and you're obeying the speed limit, then you are just driving 75 miles per hour the entire way. That would be your average velocity. However, you go up and down hills all the time. So even a cruise control doesn't keep that at 75 all the time. You've got some deviation. So if you're going up a hill, maybe your car dips down to 74 or 73 before cruise control kicks in, drops to a lower gear, and gets you back up to 75. And when you're going down a hill, your cruise control does not want to hit the brakes because it doesn't want to have to use more gas. So it will coast you when it feels like it doesn't need to use the accelerator. And then you might actually hit 76 or even up to 77. So your average velocity for the whole trip would be 75 miles per hour. But at any given moment, your velocity may be lower or higher than that velocity. So that's how instantaneous and average can be different. Now, if we look at part B, can the particle ever be at a negative position from the origin if the average velocity is positive? So there's a lot of condensation on that. So if the average velocity of a particle is positive, could the particle ever be at a negative position? So to be at a negative position, that means you have to go backwards, right? So if your average velocity is positive, could you ever go backwards? Well, that's what A just asked. Could you ever have a negative instantaneous velocity? So for example, anywhere right here, I guess that's not very good, but from from 0 to 2 seconds. So about right there. It looks like our particle is at a negative position almost that entire time frame, except for maybe an instantaneous point at 0 and 2 seconds. Everything in between, it is at a negative position. So yes, backwards motion is possible even if the average velocity is positive, because we're again looking at instantaneous position versus the average velocity as a whole. So yes, backward motion is possible. On point B right there, you are 2 meters behind your starting point. So that would be a negative position, even though the average velocity of the particle in that time frame is positive. Now let's move to the next topic. Position is to velocity as the velocity is to acceleration. So now we have a velocity versus time graph. We have meters per second in the y, and we have time in the x. You can also see that your velocity up here has an x subscript. I kind of covered that. Let's do that more carefully. You can see there's an x subscript there. So that little x below the v just tells you that this is velocity in the x direction. Nothing's going up and down. It's just on the horizontal plane. We'll be using subscripts a lot. Now, calculate the acceleration from t equals 0 to t equals 10 seconds. Now, how would we do that? Well, if it is the acceleration from one time to the other, that would be average acceleration, right? Just like how we talked in the last slide, average velocity is the velocity from one time to the other. So let's look at how we can find acceleration from a velocity graph. So we could draw a line from 0 to 10. This is called a secant line. The other was tangent, right, where it only touches on one point. But if it touches a graph on 2 points, then that would be called a secant line. So let's see if I can get a good line. Nope, missed. This is hard. All right, this might mess with the recording, but I'm going to flip this. It didn't mess with it at all. Okay, flip to my iPad real quick. Let me situate my laptop and whatnot. Okay, so if we have these 2 points right here. Okay, that was pretty close. We have these 2 points right here from 0 to 10. We want the acceleration from 0 to 10. How do we find that? So what we can do is we draw that secant line and we could find the slope. Now, how do you find a slope on a line like that? Well, like we talked before, slope is rise over run, the change in y over the change in x. So the y-axis here is v, so we want the change in velocity, and the x-axis here is the change in time, is time, so we want delta t. So how did the velocity change from 0 to 10? It increased by 4 meters per second, right? So you have 4 meters per second. And how did the time change over that time period? Looks like we had 12, I'm sorry. Oh, I drew my graph wrong. I'm sorry. That is the 10-second dot right there. Okay, so everything still holds. There was a change in 4 meters per second from 0 to 10, and 10 seconds passed. So you have 4 meters per second over 10 seconds. That would be 0.4 meters per second squared. Sorry, I ran out of room there. So that would be the acceleration from 0 to 10 seconds. The average acceleration over that time frame is 0.4 meters per second squared. Now, so like the analogy says at the top of the slide, position is to velocity as velocity is to acceleration. Velocity is the slope of a position graph, and acceleration is the slope of a velocity graph. So these have a very similar relationship. Now on number 2, it wants the instantaneous acceleration. Now, how do we find the instantaneous acceleration? So what we would do is we would need the instantaneous slope at a certain point. And we talked about that before. That would be the tangent line. So you would go to 4 seconds and do your best to draw a tangent line. Not really easy to do. Now, that is the slope that we're trying to find. And it looks like it hits at that coordinate right there. That would be at, let's see, that would be 5 seconds, 8 meters per second. Looks like it hits right here too at 3 seconds, 4 meters per second. So you can do your slope equation, or you can just look at the graph and use rise over run. Slope, you have a change in y values of 4. You have a change in x values of 2. That would give you a slope of 2. No, whoops, meters per second squared. Ignore that little squiggle by the meter. I can't undo my drawing in this program, so ignore that. So you've got a instantaneous acceleration of 2 meters per second squared, right? Now that's how you can find instantaneous acceleration on a velocity graph. Just find the instantaneous slope, which is not easy to do if you don't have a ruler, a protractor, or some way to find the instantaneous slope. Okay, so we did that by drawing a tangent line and finding the slope from that. And on number 1, we found a secant line using 2 points on a graph and found the slope between those 2 points. Now number 3, when the acceleration is negative from time is 7 seconds, right there, to time is 8 seconds, right there, is the change in position positive or negative? Explain. So go ahead and pause your video real quick and think about, is that going to have a negative or positive change in position? Okay. And you're back. So how would we know if this is going to have a positive or negative change in position? Well, if we look at the slope, we can see that the slope is negative, right? That means that the acceleration is negative. Now, what does negative acceleration mean? Negative acceleration doesn't mean you're going backwards. It means you're slowing down. So you could still be going forward while slowing down, right? If we look at the velocity value at 7 and at 8, it looks to be, it's about 8 meters per second, and you slow down to about 6 meters per second. So even while you're slowing down to 6 meters per second, you're still moving forward at a decent speed, right? At between around 7 meters per second during that time frame. So you're still moving forward with a positive velocity. Now, if the velocity dips down, if it were down here, this is negative velocity territory, right? When you are underneath that x-axis, that's when you've got your negative velocity. But since it's still positive, that means that you're still going forward. So at that point, you would have a positive change in velocity. Or I'm sorry, a positive change in position, because you're still going forward. So you're still having positive change. You're not going backwards, you're still going forward. Slowing down, but not going backwards. Velocity is still positive. So number 4, do we always have to start with graphs to calculate accelerations? No. So this can be tricky by hand, as you can see that you've got to draw lines, estimate slope to the best of your ability. There are better ways to calculate acceleration from this kind of data. Now, we will go over this in the next video, and we're going to use calculus to do it. We'll start off with algebra, but calculus is going to give you a very fast jump from position to velocity, Then from velocity to acceleration, instead of having to find slope, you'll find the derivative. So we will go over that next video. Go ahead and finish up these notes. If I missed anything or was confusing, go ahead and pause, go back in the video, rewatch it. Let me know if I misspoke or made a mistake, and I'll see if we can go back and fix that. But next video, we will go over the calculus of kinematics, specifically the derivative calculus of kinematics.